So hello everyone. So today we are reviewing PR 32247 and this is the issue tab for this PR. I hope you guys just looked for these notes and like what this PR is about. Mm. So let's open this PR in another tab and I think the font is perfect. So okay, so this PR just implements the new opcode which is check6 from stack. Uh, so currently this opcode is only available in a regtest only. It's not on mainnet or anything like Signet. It's only for regtest now. So we are just testing this opcode in a regtest first. I think later we can just publish this on mainnet. So first of all, to understand what this opcode do and how this works, like this is very interesting opcode. If you like the working of this opcode is very simple and it's very easy, but the changes it can provide is very huge. Like you can do very much new things in Bitcoin by using this single opcode, and we'll see like how you can and why. So first. Let's open this. So there is an uptech newsletter for this. Will include the font. Okay. So here you can see about the basic information about this opcode, like what this opcode means. Like it's simply like this opcode allows checking whether a signature, sorry, like whether a signature signs any arbitrary message. So if you know about like basic like verifying the signatures over a given message and public key, then you can understand about this opcode much better and clearly. So basically, if in a traditional way, when we verify the transaction, uh, so when we verify the transaction, we use a signature like over some message and a public key and a message. So first, we construct a message, but that message contains all the information about a transaction in a serialized format. For example, like the transaction version and the transaction details, output, inputs, and all of the things. So we first serialize them and create the hash, and this will turn our transaction data into some message of a fixed length. So the important point here is we are using some fixed fixed length message in our traditional way of verifying signatures. But this opcode allows us to use a arbitrary message. Means the message is not like a fixed length, 64 byte or 32 byte. Whether you can choose any like bits of message, not just like one like not just like 2 MB message. There is a restriction, but you can choose any arbitrary number under some condition. So it this opcode only needs three things, like a signature and a message and a public key. Here are three things: a signature, a message, and simply a public key. That's all we need to work with this opcode. And so, like these are the things we can achieve in Bitcoin by using this opcode, and these are very powerful things we can do. Like without this opcode, these are not possible. And we'll see. Like I am going in depth with these two. You can explore like these other like by your own. I don't have any time. Like these topics are itself in like takes a single lecture to explain, but I will try to explain in just briefly about these 2 points in detail. So okay. So the first use case for this opcode is like paying for signatures. For example, if Alice controls a private key that can sign a transaction paying Bob, then Bob can use this opcode to trustlessly offer to pay Alice for the signature he needs. So let's understand this. So for this, I have created these. I have written some scenarios here. So let's see how this works. So we are the scenario one is just simply this paying for signatures. We'll see how this works here in more detail. So let's suppose Alice has a private key. Suppose Alice has a private key that can produce a valid signature. So everybody knows we can generate signatures using private keys, and then we can verify using public keys. So here Alice owns a private key that can produce a signature. Then Bob needs this signature to complete a transaction. Suppose there is Bob, a person two, which needs this signature to complete their transaction. For example, the Alice wants to pay Bob some sets, and for example, to spend a UTXO or authorize an action. So Bob needs that signature from Alice. Okay, I hope you will understand. Alice owns some private key with some valid signature, but Bob needs this signature to complete a transaction. Without this valid signature, Bob like not able to spend his UTXO. So, but the third point here says like Bob is willing to pay Alice if she gives him the signature. So Bob is saying like, yeah, I will pay you some amount of Bitcoin if you give me your signature. So Bob is just simply saying to Alice, like, give me your signature, a valid signature, and then I will pay you some tax. So the catch here is Bob wants to make sure Alice only gets paid if the signature is valid, and Alice wants to make sure she gets paid if she gives the valid signature. So as you, like you can see here, there is a trust issue between these two persons. Like so Bob wants to make sure like Alice provide him the valid signature, then only he will get paid. She will get paid. So and Alice also wants to make sure like if she gives the signature to Bob, then he will receive their payment. So there is a trust issue. So how we can solve this trust issue between them? So there is a question like, what if Alice gives a fake signature? Yeah, like there is a possibility that Alice gives him the fake signature and Bob paid him, and then later Bob knows like the signature was fake and it's not valid. So what will happen in this case? And what if Bob takes the signature and doesn't pay? This is the other condition. Oh, yeah, like it's easy to understand. So so we can solve this problem using this opcode. Yes, FS. So let's see how we can solve this using CSFS. First of all, Bob prepares a transaction. So Bob prepares a transaction that pays some BTC to a script. For example, Bob creates a transaction a transaction and he's paying to someone using a script. And the script he used is this opcode, OP So instead of any traditional script tap script or like witness scripts, pay to sh or pay to witness script hash, he used this opcode to check like did the input include a valid signature from Alice over a message X. So this opcode simply checks did the input includes a valid signature from like Alice over some message X. There is a message, there is a particular message. So the message here is not the general message you see we construct while creating a transaction or while spending a transaction. The message here is arbitrary. Like there is some custom message. And then Bob published this transaction as a bounty. And it says like anyone can claim this Bitcoin, but only if they give me a valid signature for this specific message. So if someone has a signature for this specific message, that means this is Alice. Like Alice has some private key, and she only holds that valid signature. So Alice can simply claim this Bitcoin. But afterwards, for this step 3, you can see Alice sees the transaction, and if she wants the money, she creates the signature using her private key. This is what I'm saying. Like she owns the private key, so she can create a valid signature. That's not a very big deal for creating a valid signature because she's the real owner, and she spends the UTXO providing the signature in the input. Then the script runs, and this opcode validates that the saved signature is valid over a arbitrary message X. If it's valid, Alice gets paid, and if it's not valid, the transaction is invalid and it's not accepted by the network. So as you can see here, we use the arbitrary message, not the general message for the transaction. So Bob creates like a message. The message is just simply like including some inputs or some outputs, like creating a transaction, just a transaction-like message, and then then Bob sign this. For example, just Bob creates a message. So in this message, he includes some inputs and outputs as a which pays to him, or like yeah, which pays to him, and this output only like validate by the uh, like Alice here. For example, she owns the private key. So first, Bob needs all the information about like before Bob needs to like have some information before creating this message X, because if Bob doesn't have any knowledge about the Alice public key or anything, or like which UTXO he wants from Alice, then he can't create this message, this arbitrary message X. So that's why this whole thing works. And here it's very powerful because this is trustless. This opcode verifies all the things. This opcode takes some signature, some message, and some public key, not private key, and it will verify with some arbitrary message. So uh, this is the scenario one discussed here, paying for signatures. Now Bob paid the signature for signature. So the second one is the delegation. So for this also, so let's read like what the delegation means here. Suppose Alice might want to delegate the authority to spend her coins to Bob without explicitly creating an on-chain transaction, transferring the coins to a one of two multi-sig between her and Bob. It means that Alice now wants to give authority to spend her coins to Bob without like creating a multi-sig uh, a wallet or a multi-sig way of giving him like authority to spend the coins. Suppose Alice is the owner of some coins here. Alice is the owner, but he wants to give the permission to spend the coin to Bob without creating this multi-sig wallet between them, you can say. So how does it possible? Like how you can give the authority to spend your coins on behalf of someone without giving him permission? Like how it's possible. So this can also be done using this opcode. So if Alice designs her script, uh, this sort of delegation in mind, she can put Bob pub key in a message and use the OP to prove that she delegated spending authority to that key. So now what Alice did, so Alice created a message. This is not the general message, the default message we use to create a transaction. So this is the arbitrary message. Means this message can hold any structure the Alice wants. This message doesn't need to follow some guidelines or some like this is any random message or arbitrary message. I uh, so this is not a particular structure for this message. So what she did, she created a message and she includes the public key of Bob in this message, and then she locks the script with this opcode, and this will give Bob the authority to spend those coins or tax. So let's see the scenario two here. So Alice controls some coins on Bitcoin. Maybe they are protected by a script that checks a signature from her. So every coin is protected by a script, you all know. So and uh, for spending the certain Bitcoins, you need a valid signature. So and she wants to delegate spending authority to Bob, like temporarily or conditionally. So how she can give this authority to Bob without creating one of two multisig with Bob. So this is very interesting, like how you can give someone authority to spend some coins without creating any transactions or creating a multisig. That's very interesting. So she wants a system where she stays the owner, but Bob can spend under certain conditions she defines, and she can revoke or change the like delegate later by updating the script. So we can solve this problem using this opcode. So let's see how we can solve this problem. So Alice writes a script that will allow someone else to spend her coin only if they can show a valid signature from her over a message that includes their like public key. So Alice constructed a message with Bob's pub key in our case. So Alice constructed a message over Bob's pub key. So Alice message, for example, you can think just simple like Alice message contains only the public key of Bob. So uh, now this message like works as a delegation certificate from Alice to Bob. Now Alice holds Bitcoin in a custom script. So this is a custom script because it's working on some arbitrary message, not the general message. So this script contains logic like I will allow spending only if the spender can prove that Alice has signed a message that includes their public key and the spender can sign with that pub key. So Bob can spend the coins only if Alice has created a valid delegation signature that includes Bob pub key and Bob provides a valid signature from his private key matching that pub key. So this simply means now Alice created a script, not script, a message. The message contains the Bob's public key. Now it sends this to Bob. Now what Bob will do? Bob just see their signature and try to like now spend those coins because like Bob creates a signature again. Like Bob creates a signature for further spending those coins. Now, how we can verify that the Bob is the valid person? Because it will need Bob's private key to decode their signature, and we can just simply just Bob also provide us their pub key, so we can verify the signature is a valid signature from Bob, and we can match the Bob pub key provided by Bob himself by comparing it with the message the Alice created. So the Alice created the message which includes the public key of Bob, and now we can verify this with Bob pub key the Bob itself provides us. So first we take the Bob's pub key, and first we verify the messages not message the signature is valid using the Bob pub key, and then in the step two we verify that the pub key this Bob pub key and the pub key defined by Alice in the message is same or not. If those are same, that means Bob is the actual owner. Like Alice give him the authority to spend the coins. So this can prove that Bob is the valid person to spend those coins. That's all theory. I'm not going to explain you like all of these things here, but for an overview, this can also be useful in oracles. What oracles is? So oracles, it's just like a random box which works like if uh, if certain condition X is valid, then do this, otherwise this. So oracle is just a random box which predicts the outcome. Like if team A wins, then do this. If team B wins, then do this. So in the same way, we can use in oracles, and there is double spend protection bond. I don't want to go deep in this. And there is transaction introspection. So introspection simply means if you don't like know much about what the like meaning of introspection in Bitcoin. So simply, if you can know about a transaction in a script, this will give you the power of transaction introspection. For example, if you can know about the transaction, how many inputs or which inputs or which outputs it includes, and the version of the transaction, and all the other things, the witness fields, the signatures, all of these things inside a script. I'm not talking about like the outside the script, inside a script, inside a Bitcoin script. If you are able to identify like these information about a transaction, then this is called transaction introspection. So you can use so the this opcode also provides us the transaction prospection, because we can use any arbitrary message inside a transaction. We can include anything inside a transaction. It doesn't need to serialize the transaction and then SHA-256, D SHA-256 over some message, over some like fixed message, or the way of creating the message is fixed. So it's not like this. You can choose any message. You can use any data inside your message and just uh, sign with your private key over this message, and then you can verify with some public key. So this can also gives us the introspection uh, way of doing these things. You can read about this. It's a very vast topic. It also includes covenants. Covenants also works on this same principle of transaction prospection. So the covenants also allows us to uh, like uh, like uh, allows us to implement some more flexibility and features in the Bitcoin scripts in the Bitcoin scripts where you can send your coins and all of the things like where you can spend your UTXOs and how long does it valid for, and all of these things you can do with these. So now let's go with the code. That's enough for theory, I think. So let's see the code. So here we are just initializing our new opcode here. Like the taproot is also defined earlier, but this is new opcode like CSFS. They are defined here, and that's an invariant of an enum. And then here also same, we are just introducing our new opcode. So this is interesting. Uh, Wait, let me open this in my VS Code. Yeah, okay. Let's increase size. I think that's enough. So, so what? So this is the code. So, okay. So this is the new code. That's the existing code there. So this code defines like when a node signals for this new opcode. So if a node wants to signal for this opcode, they can choose simply bit 1 while signaling. If they can, if they use this bit, they that means the node wants to signal for for this CSFS opcode, and this is the start time. For example, it's in regtest, so there is uh, no boundation here. It's always active. You don't need to active this by manually or anything like this. It's always active in the regtest, and there is no timeout. Uh, like there is no boundation like after a certain period, this opcode is invalid by the nodes or anything like this. This will not happen by this, no timeout. And also the minimum activation height is 0 here. So we just simply start with uh, using this opcode without any conditions in batch test. So from the node 0, you can start this opcode using in your script. So there is no boundation here. So this code just simply update some consensus over this opcode. And there are some policy changes here. We are again defining two variables here. So this is the discourage upgradable pub key and this opcode like check from stack. Not important. Yeah. So here we are defining. So one more thing, like this opcode works on TypeScript only for now. Like it only use pub key as X only pub key, not any other format of pub key is allowed right now. You can only use the X only pub keys uh, to work with this opcode. So here we are just changing some lines. For example, here we are updating the message data and message size constraints here. For example, in the below, you can like before, it's bounded to use the message size of 32 bits or not bits, bytes, 32 bytes. Now you can use message.size, like it's the arbitrary size of message. There is no boundation here. There are some boundation on the transaction level itself, but there is no boundation here. And we are just passing the message data here, and you can see the change in sizes of the message. It's the arbitrary message, of course. So there is nothing much here. We are introducing span here. nothing else. And yeah, so this code validates this new opcode in only regtest. If we are using regtest, then this will activate this opcode here. And if you are using mainnet, signet, or anything else, then this opcode will not work. So this line of code only checks here, like it's only works inside regtest, not in the mainnet or anything else. So that's the interesting function here. Let me open this function in the VS Code. The source is script inside source and script which interpreter. Oh, it's already open here. Okay, yeah. Okay, so that's the one of the main function that defines this opcode here. So the function name is eval check sig from stack, and you can see the argument it takes a signature, a message, and a public key. Well, that's a X only public key, not any other type of public key, and some data flag, and uh, and then the version, and then the error. And for success, it's the Boolean variable whether the script is successful or not. And if there is any error, we catch this by using the script error. So we are checking if signature is not empty, this will make this success toggle. So if signature is not empty, this line of code return true, and then the negation becomes like turns the true into false. Now the success is false here. So, but yeah, let me repeat. If signature is empty, this this line becomes true, and then the negation becomes false here. So that means success like becomes false. And if it's not true, if signature is not empty, then the success becomes true here. So we are not moving if signature is empty. We are just returning some like we'll see here. If it's not true, so we'll just exit with some error or like without success. So here we are checking like this is script only. So as I already said, like this is only the part of TypeScript. This will not work with any other script we have in Bitcoin. So this is the part of TypeScript because it only uses X only pub key, other nor signatures and all. So this is the part of TypeScript, not any other script types. You can, yeah, you can check here. There are four versions here: the base version, the witness version, the taproot, and TypeScript. So this is valid in on TypeScript version. Here you can see all the information about this in the BIP 342. You can explore by yourself. So we are some just checking some SIGOPS and witness size ratio test here. These lines are just doing some checks, some ratio test here. If it's successful, we'll move further. If it's not, we are just uh, throwing an error and saying this, like validation rate is not met. And then here, if pub key size is zero, like if you provided a pub key with non-zero length, then we are returning an error here. So your pub key must be equals to the exactly 32 bytes. In the LZIP code, you can check here the pub key needs to be exactly 32 bytes. If you don't have 32, if you don't provide the pub key of 32 bytes, this will simply return with error, and then we are providing the signature, and if the signature is not 64 bytes, this will also return with some error. So the signature also needs to be the 64 bytes, and we are creating the instance of x only pub key here, and now here we are verifying the pub key with over some arbitrary message x, you can say. So in this function verify nor show like nor, we are passing the message. The message length is not like uh, bounded by anything here. You can see there is no condition which bound the size of the message here, and we are providing the signature here, and then we'll verify the this with respect to this pub key. And if it's not true, yeah, this simply returns some error. And these are some flags for modifications, and also like uh, if you pass any other pub key type, this will simply return error. On so currently now only X only pub key is validated by this script and nothing else. So that's about this function, and we have covered this. Yeah, there are some checks here. Okay. So here we included a case in the switch statement. The case simply means, so if we are using this opcode, then simply check if the SIG version is like initialized to the base or witness. If it is, then simply return the error, because as I said, the opcode is only valid for the TypeScript version. So if you use any version uh, uh, other than the TypeScript, then just it simply returns the error. So here we are creating a stack. No, like we are not creating a stack. We are checking if the stack contains less than 3 items. If it is, then return the error. So it needs 3 items: signature, message, and public key. You need to provide 3 things, and if there is less than 3 things in the stack, this will simply return with error. Here we are just initializing the variables from the stack. We are popping the we are not popping the stack. We are just initializing those variables from tag. For example, from the like in the index -3 in this stack, we are fetching the signature. From the index -2, we are fetching the message, and from the index -1, we are fetching the public key from the stack. So if we have 3 things, we are initializing this success variable here. Now we'll just simply pass these things in our eval checksig from stack function. This is the same function we just saw above. So this is the same function. We are passing these 3 things: the signature, message, pub key, and you also know like how this function works. It just verifies the signature over these 3 things. We also pass some extra things like flags and version, and these 2 things for error, catching errors, and then for the success. So after this, if this function returns anything else, like if it's not returned true, we return false at the end. And after all these operations, we are popping this stack. Uh, so after copying the stack, we just push the stack with the success or false. So whether the all the message or message is valid, or the signature is valid over some message using some private key. If it's true, then we are just pushing back one, otherwise zero. So yeah, that's all. And that's the default case. If anything else uh, is happened, then we'll just return the error and say it's a bad opcode. It doesn't exist. That's about this function. And yeah, this is also the things like it's checking if the opcode is this. If it's this opcode, then we'll check with some flags. If okay, so if we uh, like if we turn this flag to true, like if we don't want to use this opcode, we can turn this flag to true. And if we did, then this will simply return us the error, like like we don't want to use this opcode. Otherwise, otherwise we just send the success to the user. Anyways, if it doesn't provide any information about if it's not discouraging this opcode, then we'll just return success. And in any other case, we so like if it's discouraging this opcode success, then we are returning the error. Otherwise, we are returning the success in every other case. So that's all. And there is a test also. These are some just adding the variables to know about Bitcoin, like this new opcode exists. It will adding some case. So these are the tests you can see here, just defining some data here. So some valid or invalid data both, like test the above script. So just this will simply checks like if we are not running on regtest, and if we are not signaling for like the deployment this CSFS of code, then continue because it's only like made for working on regtest. And these are all the checks to check the chain type, whether it's regtest or not, or whether we are using these flags or not. Then just simply update the script verify flag. And there is a test. Yeah, I want you to explain a little bit. So yeah, so these are some lambda expressions here. So I'm explain you the like few of them, but you will get the idea like what is this about. So we are creating a lambda function here, and just here represents the number of operations. PK stands for the public key here. We are passing these two things, and we are creating a object of this C script type. So what we are doing in this, we are creating a script. First operation is drop drop some data from the stack if it's exists if it's some random data in the stack, we'll drop this. And then uh, we are pushing a signature into the stack, and then the message into the stack, and then the public key into the stack. And then we are duplicating these uh, three things, and then we just run our this opcode, like op checksig from stack. This will do the verifications as written in the above function. And then at last we drop all the things from the stack, and we do these things n times. Here, like the n we provided here is the number of iterations we want to use for this operation, and afterwards like we are dropping and repeating this n times. That simply means for these functions, I know you got the idea uh, about these lambda functions. Same here, we are creating a C script object. We are pushing like first we are dropping from the stack. We are passing the public key, and then this opcode checksig verify, and then we are passing the signature and then message and the pub key. Again, we are doing some duplication from the stack. Sorry, duplication from the stack, and then we are just testing with our newly created opcode, and then we'll drop all these things and do repeat all the things n time here. And here you can see all the signatures are non-empty here. So the signature we push here are non-empty and they are valid. And here we are just pushing one empty checksig and one empty OP checksig from stack. So we are just pushing all these things, and we will verify like whether the node returns or exits or with an error or not if we provide some empty data in this stack. So uh, so this is the script just creating the private keys, two private keys, and then the respective pub keys, two pub keys from that private keys. And then we are creating a message. The message is random, generated using random bytes. Here the foundation for the message is 520 bytes, and we are just uh, further splitting the message into the three or four types, like the truncate message, like we are just removing the first byte from the message, and in the extendable length, we are just extend the message with some like additional size, and what like other CSFS message means generating the message randomly. It's a truly random message. All of these things, and here we are generating a random pub key, and the pub key is to be the size 32. If it's not 32, we'll return with the error, as I shown earlier. So okay, and simply, yeah, just we are here just same passing the message pub key and then the opcodes and the further opcodes, and we'll check if it fails or not. And like this will test the simple CSFS, and this is the valid. This script should pass the test, and this script should fail the test uh, because we are just passing some uh, like unknown or wrong information here. So we are just passing some unknown pub key here, and then with one arg, two args, and then the empty public key we are passing. We aren't passing any pub key here. Like you can see, OP0 opcode is just simply nothing. So we are just pushing some empty data into this stack. So these splendors just run these scripts by passing the inputs. For example, like the getter, like the inputs we generated earlier here. All these inputs generated here will pass using the standards. For example, you can see the getter sign will pass the signature we created, and all of these things. So just these spenders are passing the input here, nothing else, and this will check if it's failing expectedly or not, like, and what are the uh, error we will receive after failing. So if stack fails and give us these error codes, that means our script is working fine. Otherwise, it's not. So this will compare the errors with these error codes, like this error in our signature. Like we are passing the invalid pub key here, as I said, like empty public key, and then we accept an error. So the error here is this error, like in our signature or something like this. So that's all. I think, yeah, that's all I want to explain to you. And let's back to the question. So let's start with the question one. What do you understand by this new opcode CSFS? Anybody wants to answer? I'm audible.
Yeah, you're
Are you-
audible. Op,
Okay, okay. Anybody
uh,
wants?
yeah, am I audible?
Yeah. You are audible.
So basically, op check sig from stack. It's a new opcode for Bitcoin script, and
Yeah.
it enhances the basically it increases the flexibility and it by allowing the verification of the signature over a message. Uh, Previously or
Yeah.
traditionally we need to hash the uh, transaction bytes, and then we need
Yeah,
to
like
verify
yeah,
with the
like
signature.
yeah.
Yeah,
We
now
have this like yeah. Continue. Sorry.
yeah, I mean, I was just saying, yeah, we need transaction hash, and we need to hash the transaction bytes and then verify it with the signature. But now we can just provide the it with the message, arbitrary message, and later we can just verify the signature.
Yeah, exactly right. So just it simply means we can use any arbitrary message now. But before we need to use a specific structure of a message. Like the message is created previously by looking the transaction contents and serialize them and then destar them. So now you can choose any message for the verification. So uh, now let's proceed with the question number two. How can proposals like covenants be beneficial by this opcode?
Governance, I'm not aware of that.
Yeah, I'm also not aware by covenants. So yeah, but generally, okay, I will explain. So the covenants also provides us the way to verify, like to give us the more flexibility in the Bitcoin scripts, so we can do these type of things like the arbitrary message, and we can see like how the transaction looks like in the Bitcoin script itself. So I want to give you a uh, very good example if you can understand. So the example is, suppose in the message, in the arbitrary message, we just pass a whole transaction hex, like a transaction hex, a serialized whole transaction hex, contains all the information about the transaction from the version to the sig hash and all of the flags and all the inputs and outputs. So let's imagine we pass the transaction hex in that arbitrary message, and we use this message to generate our signature. Now, if you send this message to someone else, so someone else using scripts, so what we need, they'll need some message to verify. So when he receives this message, now he don't need to look at the uh, transaction info, like any transaction information. He receives the message and it contains the transaction hex, a whole transaction hex, and this can allow a node, a script, to know about a particular transaction without looking like anything outside of this script. I think you can understand.
Yeah, I mean, this will be it will reduce the computational power of calculating the
Yeah,
transaction. Yeah, right.
yeah, right,
Okay.
yeah, right. And this is more flexible. Like you just receive some inputs, and by looking at the message, you know how the whole transaction looks like. Without ever, you don't need to fetch the transaction. You don't need to anything like do anything else rather than just looking at the message. And the message contains whole the transaction hex, and you know how the transaction looks like without looking anything else. Otherwise, you need to fetch the whole transaction by passing with some RPCs with transaction hack, and then you will receive some information. But now you have already this information. So let's move to the third question. So which SIG version does this opcode check from stack use? That's very easy.
Yeah, version 3, I guess, TypeScript.
Yeah, yeah. So question four is, what does the function eval check sig from stack do? Okay, I will open the function for you. This function.
Yeah, I mean,
What this
it
function?
just check the version, public key size, and evaluate basically the contents of the uh, opcode. I mean, what's inside the opcode. Just evaluate
Yeah,
everything.
yeah. So this will look here, yeah, the pub key and the size of the signature, and but it doesn't checks for the size of for the message because you can use any size of the message. For the message. Okay. What does the okay? We're done. So the last question is, what will happen when legacy nodes don't recognize this opcode?
Uh,
So the answer for this question is here, I think.
will it make the transaction invalid or
No, no.
it won't? Okay.
Wait. I will show you. Where is the code? Yeah, I think here. So like, if any node doesn't know about the this opcode, then it simply returns success for this for that node. So if any legacy nodes uh, receive any transaction which use this opcode, then it just simply make it valid without saying anything further. Like here, this line of code do this. Yeah. So it's automatically that success for those nodes who don't know about this opcode. And but the nodes which use this flag, the flag name is script verify discourage exit from stack. If they use this flag, then they simply return with some error because the node itself explicitly uh, signaling not to use this opcode. Then only this opcode, this error is like transferred by that node. Otherwise, it's just simply success. That's the question. That's the last. That's the
But
answer
if
for the
we
last question.
the code change, legacy
What?
node won't compile this part, right? They won't run this check. If you see the red one, it will just return the set underscore error. So will it make the I think it will make the transaction invalid. I mean,
Yeah, I
if
think this will make the transaction invalid for that node
yeah,
because the message is not verified uh, by
yeah.
that node. Mm,
But
that's about translation. But these statements need more further review, I think.
Yeah, yeah.
Yeah. Um, I've reviewed but not so with uh, serious carefulness. Like I just reviewed it quickly, but yeah, it needs some careful review.